Question number 7 is from the 2015 AP exam, and it says f prime is the derivative of a twice differentiable function, so that's what's given here, and of twice differentiable function f. Okay, so twice differentiable means that the second derivative of f is continuous. So we have the derivative is smooth and continuous, and the second derivative is continuous. F prime has horizontal tangents at -1, 1, and 3. So I'm just going to sketch those in. So at -1, we have a horizontal tangent here, a horizontal tangent here, and a horizontal tangent here. Okay, so what that means is that the second derivative is equal to 0 at those points. The areas of the region bounded by the x-axis and the graph of f prime between -2 and 1, so I'm just going to highlight that, between -2 and 1 is going to be this area in here, and that's equal to 9. Okay, so that's going to be an area of 9. That's an area of 9 units there. And from the area between 1 and 4, the area is 12. So this area in here, I'm just going to shade that in. This area in here, this area represents an area of 12. Okay, and they're both below the x-axis. So part A says, find all the x-coordinates at which f of x has a relative maximum. Okay, so we're going to find that. We're going to test our critical points, and our critical points are going to be where the graph of the derivative is equal to 0, or the slope is 0. So at -2, we have f prime is equal to 0. On the left, it's positive. On the right, it's negative. So we know it's going up, sloping up, 0 slope, and sloping down. On this side, we have another 0 at x equals 1. So at x equals 1, we have another 0. Okay, so it's going to be a slope there. But on the other side of that, it's going to be negative still. So it goes from negative to negative. So still sloping down like this. Okay, so that looks like it's a slide to that point. And the end point at 4, we also have a 0, but we don't know what's happening on the other side. So find all the x coordinates for which f of x has a relative maximum. Well, that's going to occur at this point right there. So at x equals -2, we have a relative max. Okay, so we can see that based on our slope chart. Part B says, on what intervals contained in -3 to +4 is the graph of f both concave down and decreasing? Okay, so we have our decreasing regions here. Just going to highlight them. We have decreasing regions here and here. And we need to test the concavity. Now, when we look at a derivative function, where it's sloping down means the derivative of the derivative is negative. So we have sloping down points, and that's going to be based on where it changes direction. So at -1, we know that it changes direction. Okay, so we have, in fact, we have a 0-second derivative. On the left-hand side of that -1 value, it's sloping down. So it's sloping down, which means that the second derivative is negative, which means it's concave down. Between these 2 points here, so between -1 and +1, we have sloping up, so that means we have concave up. Okay, and then second derivative is equal to 0, so we have a horizontal tangent, so second derivative is equal to 0. It changes direction again. And between 1 and 3, it's sloping down, so it's going to be negative concavity. And then from 3 to 4, it is sloping up, so it's positive concavity. And again, we have a horizontal tangent. That means the second derivative is equal to 0. So we need to know where the graph is both concave down and decreasing. Well, we figured out the decreasing regions. We also need to figure out the concave down regions, which are these ones here. So where's both concave down and sloping down or decreasing is going to be, it looks like between -2 and -1, it's concave down and decreasing. So I'm just going to find this overlap here. Okay, I'm going to do this in yellow. So between this point here and this point here, between -2 and -1. Okay, so it's concave down and decreasing in the interval -2 to -1. That's one interval. And it looks like there's another interval here where it's concave down and decreasing. That's going to be between +1 and +3. So the other interval is going to be from 1 to 3. And these two intervals is both concave down and decreasing. Where we find inflection points is where the graph changes concavity. And it looks like that we have 3 points which we can check. And in all 3 points, the direction of the concavity changes. So we're going to have inflection points at these coordinates here. So there's an inflection point, there's an inflection point, there's an inflection point. So at x equals -1, +1, and +3, we're going to have points of inflection. The last part of this problem says that given that f of 1 equals 3, use an integral expression to find f of 4 and f of -2. So first of all, to find f of x values, we can generalize with this expression. So the f of x is equal to some starting point, f of a, so that's our starting y coordinate at a, and then it's going to be the change or the displacement in f, which is the area under the derivative f prime. So if we find the area from a to x, that represents the change. So we can kind of look at it like this. This is a start, the starting y coordinate, plus the change in the y coordinate, which is the change is going to be the area under that curve. That's going to give us the final y coordinate f of x. So that's what we're going to do. We've been given a starting point at x equals 1, y equals 3. So if I want to work out the value of f of 4, I need the starting point. That's going to be y equals 3 plus the area under the curve of the derivative from x equals 1 to x equals 4 under the derivative f prime function. Well, we have the f prime function here and the area under the curve from 1 to 4. So we have to start at 1. We're integrating to the right. Okay, so we're integrating from 1 to 4 this way. Oops, that's the wrong way. 1 to 4 in this direction. That means that the area under the curve is going to be negative. So we're going to consider that to be -12. So the displacement is going to be -12. So it looks like this. My f of 4 is equal to 3 plus the area under that curve is a displacement of -12. Okay, so then the coordinate at x equals 4 is going to be -9. So f of 4 is equal to -9. We can do the same thing for f of negative 2. So f of negative 2 is going to be equal to the starting coordinate, y equals 3, plus the area under the curve from 1. But in this case, we're going backwards to negative 2. Now, this is going to be an issue we have to be careful of. So that's under that f prime graph. Now, since we are going in the opposite direction, starting at 1 and integrating this way, the area under the curve is going to be the opposite sign. So although it's under the curve, the displacement going right to left is going to be positive. Left to right, it would be negative, but right to left is going to be positive. So that's going to be plus 9 is our displacement. So then the coordinate, we work it out as the starting position 3 plus the displacement is plus 9. So we're going to go plus 9 is the area. And so the y coordinate that we end up at is going to be 12. So f of negative 2 is equal to 12.